Hello and welcome back to Calculus. We're going to be doing Lesson 10, Limits of Trigonometric Functions. Now, before we begin, we're going to have to recall the following trigonometry identities you may have learned in your trig class. So, what is sine of alpha minus sine of beta? Well, it's actually equal to 2 times sine of alpha minus beta over 2 times cosine of alpha plus beta over 2. Okay, so now that we have this, and also, that sine of pi over 2 minus x is cosine of x. Now that we have these two, we're just going to put it in our pockets, and we're going to come back to it later. So, we're going to try to prove this lemma here, and that is that locally at 0, sine of theta is less than or equal to theta. Now, what does it mean to be locally at 0? Well, I'm talking about theta as the angle, locally at 0. So it would be like around 0 in some interval around 0. There exists some interval around 0 there. Such that sine of theta is less than or equal to theta, the absolute value, I should say. And I'll show why this is the case. So here's a proof. Case 1 is that if theta is between 0 and pi over 2, in that case, we'll only look at the top triangle right here, this top, and the area of the triangle is, of course, less than or equal to the area of the sector, and it's only equal to the area of the sector, of course, when both of the areas are 0 exactly. And the area of the triangle is 1/2 times 1 times sine theta. Since sine theta is the altitude, we're just using 1/2 base times height formula, and that's less than or equal to the area of the sector, which is the formula theta over 2 pi times pi r squared, which is 1 squared. And we'll get from that sine of theta is less than or equal to theta, but recall that theta is in the interval 0 to pi over 2. So sine of theta is also positive, and theta is positive. So theta is positive. So the absolute value of sine of theta is equal to sine of theta, which is less than or equal to theta, which is equal to the absolute value of theta. So we've proven the first case of our lemma. So case 2, theta is between minus pi over 2 and 0. Again, we're going to do the exact same thing just for the bottom triangle and sector. And we're going to get 1/2 negative sine theta, and all that's going to cancel out. And we're just going to get minus sine theta is less than or equal to minus theta. But since sine and theta are both negative, we'll get what we want. That's the absolute value of sine is less than or equal to the angle locally at 0. It's very important that it's locally at 0. We cannot make this construction unless theta is sufficiently close to 0. Here's a quick remark. That is that if we have theta to be x minus x naught over 2, where x and x naught are real numbers, then by the lemma, 2 times the absolute value of sine of x minus x naught over 2 is less than or equal to this, of course. And we know by canceling out the 2's, we get the absolute value of x minus x naught. So we know that this being less than a positive number epsilon, and we'll see why it's useful later, implies that 2 times sine of that has to be also less than epsilon. Okay? So, what does that mean? Well, we're going to move on to our proof. So, theorem actually. The limit as x approaches a real number of sine of x is equal to sine of x naught, which also is a real number. Now, recall the epsilon delta definition of this limit to be as follows. Therefore, for our proof, we're going to fix epsilon to be a positive number. I'm going to write a conclusion, which is implied by sine of x minus x naught, the absolute value of that, which is equal to, by our, handy trig identity, that we pocketed, this, and that's less than epsilon, and that's the product, so we're going to split the absolute value to the products. And notice that cosine of this angle, cosine of any angle, the absolute value is less than or equal to 1, so we can just remove that here and just multiply by 1. And by our lemma, remember the sign is going to be less than just the angle. So, of course, we're going to just write this here, and the 2's and the 2's will cancel out. So we're just going to get this is less than epsilon, which, what did we know that can be implied by 0 being less than the distance between x and x naught, which is less than epsilon, and we'll just choose that to be our delta, and that is our proof. Now we're going to prove a very similar theorem for cosine. And we're going to pause here and actually take some time to think about it. Well, we know that the graph of cosine is just a horizontal shift by some units, in fact, specifically pi over 2 units. And since we know this is true, what does this mean? Well, I mean, of course, if the limit of sine is just plugging it in, then of course the limit of cosine is just plugging it in. So we don't need to do any epsilon delta things. We can just use the other identity that we pocketed. So the limit as x approaches x naught of a real number of cosine is the limit as x approaches x naught of sine of pi over 2 minus x, this difference, which is equal to the limit as x approaches x naught of, we're going to compose sine of x and pi over 2 minus x. That way we can use the limits of compositions to get that the limit as x approaches x naught of pi over 2 minus x of sine of x is equal to just the limit as x approaches x naught of pi over 2, x approaches pi over 2 minus x naught, remember, real limits of polynomials. And by the real limits of sine that we just proved above, it's just sine of pi over 2 minus x naught. We're just going to do the exact same property in reverse, and it's cosine of x naught. And we're done. And we're just taking, the fact that cosine is just a horizontal shift of sine, and calculating the limit for sine, and then just converting it back to cosine. That's what we're doing. Final theorem, and that is that if x naught belongs to the domain of tangent, so it's very important that tangent, that x belongs to the domain of tangent, or in other words, cosine of x naught is not 0, right? That's the only time that those are the only holes in the domain of tangent. Then the limit as x approaches x naught of tangent, where x naught is a real number, is just tangent of x naught. This proof is really trivial. You just have to use the quotient rule, recalling that tangent is sine over cosine, and we get what we're looking for. But remember, cosine of x naught cannot be equal to 0, but we know this is not true since x naught is part of the domain of tangent. And that's our proof. So you don't really have to know the limit of tangent. I just think it's important because now that we have all this, everything else is also easy. Really, sine and cosine are the building blocks of the other trig functions. So hopefully this helped you guys out, and good luck in your studying.